Can you hear me? Cool. Yeah, so for those of you who don't know me, I'm Simon Holmdahl, as Chris pointed out, and we're both older. I'm a partner and director at a studio in London called Panoply. We are remote, so we kind of like, our headquarters are in London, but we are a remote studio. We have been operating for 10 years now, believe it or not. So again, on theme with the whole getting older thing, which is great. And for the first time, we actually have a reel, because we never had one before. So that's funny. So I'm going to start by playing the reel, and then we're going to dive into some projects, some R&D stuff, some tinkering and stuff like that. And hopefully it's interesting. I don't know, because you get clueless yourself when you do this for a while. You know, when you start building something up and you haven't really tested it on people, if that makes sense. All right, so here's the reel. Enjoy. Panoply, 10 years in the game. Celebration. Anyway, so I'm going to start by talking about, I've been doing a lot of talks in the past on various weird subsolvers and strange systems. And there was this one thing that everyone kept doing that I didn't touch. That's Vellum. Have you heard of it? So I decided I was going to try to do something with Vellum, but I wanted to do something a little bit that I felt that would compel me to do it, because I felt like we've seen a lot of inflated balloons, and nothing wrong with that, but I wanted to try to do something different, but we all, I guess. I'm also a kid that grew up with an old Atari, and my friends have Amigas and stuff, and we were playing around with this cool graphics demos and stuff back in the day, and I was always really interested in the aesthetics of these things. So this is a little bit of an homage, and it probably doesn't show up here, but I've been basically making sure that almost every slide looks like it's shot on a CRT monitor, which is completely stupid. I shouldn't have done that, because now my entire thing is like 40 gigs here, but whatever. And you get loads of banding, so that's great. That's another benefit of this. But yeah, this project Manifold started as an excuse to learn Vellum, but also I wanted to kind of try to intersect higher dimensional objects with the two-dimensional planes. If you imagine an intersection of a scanner that scans an object, you would get the shadow of that object in 2D space. And then the thinking was that if I can have these different objects and they're all have different material properties assigned to them, when they then get scanned, if you will, they would then modify various properties of this Vellum surface. So that's the 2D to 3D intersection of these different realities. So that's this exact same. This is the first test we did on this, which was, again, it was just literally a cube where we trapped a bunch of spheres and cubes. Again, keeping it. I like the simplicity of keeping simple primitives. So, and then again, using that to then modify the various material properties on a texture level for the both texture, but also simulation-wise. So that kind of spawned this, and I also like the idea that if you're looking at this, it's so flat. It's almost no perspective in it at all, which made it feel like it was, they felt trapped in a flat dimension. It kind of felt appropriate. We also did some alternative materials. This was like a little collaboration with GSG. So we used their material collection. So this is like the performance fabrics collection right here. So this one is both wind resistant, waterproof, and all of it, if you will. And then we started playing around with this. So we started mapping it onto, I just like this kind of idea of abstractly visualizing these different dimensions. So putting a 2D object in a flat plane in a 3-dimensional space felt kind of appropriate. So just slapped it in a cube and started spinning it around. But I also wanted to do something with, I mentioned scanning objects. So that was the initial test. And I thought, if we can build some sort of contraption, imagine we're in some weird testing facility here at Panoply headquarters near Area 51, and we're simulating all this zero gravity, anti-gravity thing, and we're tracking all that data, recording all of the parameters of these objects. We build a scanner, and then we basically, normally when we work in Houdini, we generate a lot of data, and it can sometimes be, I don't know if you've had this, but where you visualize it, you just click the kind of visualizer and it shows us colors or indices, and it's kind of a shame that that's not visible, because sometimes that actually looks really cool, just the data itself. So we wanted to expose the data here as well, which is why this project felt like a good excuse to do that. We also included a checkerboard sphere. For those of you who know, you know what that means, but Amiga, yeah. No one knows what Amiga is there. Okay. Some of the initial tests from this came out from scanning them was here. I thought it was pretty cool. Like, again, each little piece could have its own properties to be transferred. It can also be velocities from them that can then transfer. But that was just the initial test. So now we have this scanner that lives in this world. We render it with a bunch of different AOVs, and we also added this rotation to our scene as a way of like linking all these different realities together. The whole idea is that there's a visual connection between the scanner and the data that is visualized, and we want to show it together. So by introducing a simple narrative rotation, basically, it kind of ties the different layers together. So here you can see, again, another homage to the Commodore with those screens. And then we have the third scene, which was basically the square, the fabric that's suspended in, and visualizing that data as a live connection. So that was all well and cool, but I felt like the more we did it, we kind of started exploring these different data visualizations. And the more I just started like, the data kind of looks cooler almost than the rest. So just like started playing around with some alternative structures and stuff. So we can see there's some additional scenes here. We have the original cube thing, and then we created some 3-dimensional structures that, instead of like tracking a 2-dimensional space, it's kind of tracking another dimension in a weird way. So if you look at this, for example, instead of now scanning with a physical object that moves through it, this is essentially almost refracting another version of the reality, which basically you shoot like a ray from the smooth normal of the external surface, and then it kind of creates these distortions and bends that then affects the fabric. So it's just adding one little extra layer to your vellum simulations, basically. And this was running through a top network, so you could we ran a bunch of wedges and got a bunch of different structures. And the same thing is true for this thing, which is more of a rigid structure, just based on a Boolean that's just creating these structures. Very simple. Here's another one. When it comes to the data as well, we wanted to, further bring an homage to the kind of retro computing and the early days of where data felt much more raw and direct. I don't know if you ever operated these old machines. You plop on it in the flop, and it's almost like instance. It's all from ROM. Didn't really have an operating system or anything. So this is a console readout that completely, I mean, shamelessly, we used ChatGPT to generate this kind of gibberish. As we gave it a little bit of background on, oh, this is a simulation at Panoply headquarters. We're doing some anti-gravity experiments and so on, and it just wrote up a bunch of gibberish. And here's another one. You can see a little bit more natural sim, and has files. I don't even know, but if you pause it and read it, it has a lot of interesting little bits in there. And then at the very end of the film, we also made like a kind of one that crashed, kind of, so you can sort of see it starting getting corrupt towards the end there. So that was really cool. So this was actually, we're going to talk about it a little bit more, because this is a little bit of a theme. Like, I don't know how you guys are feeling about AI, but it's been terrifying at times, and then you kind of feel a little bit better, and then whatever. And this is an alternative way of working with it. Like, there's no prompt to image. It's just using the AI to like help coding stuff, essentially, or write up stuff for us. So, and then this, the title, the end title of the film, which was done using the new Copernicus as a way of bypassing the rendering process. And it's just really nice to be able to much easier record data to textures. I mean, I've been doing it for a long while with the old COP system, and I'm still kind of like transitioning into the new one. I feel a little bit more comfortable with the old one in a way, but it's cool. So I'm going to show you just how simple this was to set up, and I'm going to talk to it like in a very simple way, so you can sort of see. The first thing we did was just type out the type, and then we fixed the kerning because it was awful, just with an edit. And then just slap some UVs on there, which is just a frontal projection. And then you kind of shrink the logo down so that it's just really, really flat. And the reason we're doing this is that we want to scatter points and fracture the geometry later on. And when we fracture the geometry and it's really flat like that, we get really stretched kind of cuts, which creates like a very vertical, obviously, stating obvious, vertical cuts on the geo that feels kind of like streams of data. Then we use a kind of divide to create a bricker style to recreate the kind of blocks that then later on becomes the different parts. And from this we then, because we're basically sorting by y, the y coordinates, and we're changing the geometry upstream with the scatter, so it's always changing the order ever so slightly, and that introduces a natural glitch to the system. And using this y coordinate, we can then use that as a mask for our transition. So yeah, so this is how that entire effect comes together, as in the motion of it. All we're doing here is we're sampling that fall off, which is just the relative point number between the min and max points of this packed, and I should say all these polygons got packed. And then using a power function and a strength, we can then just displacement along an axis. And the thinking here is that it kind of mimics the scrolling consoles visually, but it's also, you know, coming together very, very much, quite literally. So it's a very simple and powerful method of kind of explaining that. And if we're looking at the actual network of this, I kind of had to like bend it around a little bit because otherwise it wouldn't fit. I didn't want to put it sideways. So, but it's nothing special. It's literally what I just explained. So, you know, just type and then edits and then scatter, fracture, and so on, and then packing the points. So after that, we can now load this into Copernicus. So this is a little clip that shows that. So this is just a little messy graph, but yeah. It's, in general, what we're doing is we're just taking a camera and we're reading out color and UVs and ID. And then we're just mapping, we're literally just mapping shapes, simple SDF shapes that we convert to monos and then tile them in different ways and map them to the UVs. And then we're using that very, very simple gradient that was used for the transition and just remapping ranges of that to mask it essentially. And you can just layer up this gibberish complexity that kind of looks like corrupted data, which is the whole idea. And then we render them out as separate layers and then composite them afterwards. But at least the rasterization part, there's no render time here. I mean, it probably wouldn't take that long, to be fair, to render this in like Karma or anything else either, but you know, it's just nice and direct. So that gives us this. And so, you know, when we, as some of you might know, we need to tell people what we're going to talk about in advance when we do these talks. And so I asked ChatGPT, like, what should I talk about? And they were like, oh, your talk should be called Manifold Realities, and it should be about manifold. And so I was like, oh, shit, okay. So then I guess I'll do that. But then on Monday, or Tuesday, when I started thinking about this presentation, we've been very busy, thankfully. I was like, how can I build upon this further? So I thought to myself, how can I expand this concept of multi-dimensions, many realities and stuff like this? So I thought, what if, as an experiment, I've been doing a bit of like, we talked briefly about kind of the AI and how it's affecting our work. I thought maybe I can use AI to retrieve external data. I've never done it. I know it can be done, obviously. If you know Python and stuff, you can probably like do some stuff. So I literally just had my conversation with the AI overlords as I was out walking in the morning. And I decided, can we kind of read like weather data? Maybe. I mean, it's kind of on the nose, but you know, whatever. Start somewhere. So maybe it could be possible. And I decided that when I get home, I'm gonna give it an hour or half an hour and see if I get a little bit of something out of this. So my first plan was to just ask, can we read a lat-long coordinate and a date and time, and then somehow get wind and speed, temperature, any sort of data from this? And ChatGPT has this function as well that has, you know, deep research where you can go out and search the web and find information and compile different things. So I did that with it, and it kind of came back with a few options. I very quickly decided to just use Open Weather. It seemed to be the easiest one. So I signed up there for an account, and then I had an API key so I could feed it into Houdini. And I then asked it to, you know, write a Python script for me. So I was like, please now, can you make a Python script that kind of creates a point with that holds all these attributes that you can download from any coordinate that I give it. And that worked. It was actually surprisingly easy. So after I got that, I was like, okay, but 1 point and 1 time is not going to be a very interesting simulation. So I need to map this, and I knew I had I think you have about 900 or so API calls per day on this thing you can use. So I was like, okay, let's try this. So if I do a 10 by 10 grid, that's 100 API calls. And then I do a few different time slots. It very quickly adds up if you do the math. But I decided that if we can modify the Python script so that I can read in the lat-long coordinates of a center location of a square grid. So if you imagine you're creating a grid of points, each one has, in this case, 10 by 10, 100 kilometers apart. And then I send it the API key, the date and time that I want to sample. And then I run it through a top network. TOPS, I don't know if you're familiar with this, but it's a very, very nice way of sending like attributes down chain and like almost parallelize your reality. Very, very on brand for this talk in a way. So I decided I'll do four time slots, a few hours apart. So, and then I do a 10 by 10 grid. So I ran that. It worked fine. It generated a grid of points with all these attributes. And I decided that I would just blend them together. So I took all the relevant attributes blended them, just lerping them over time, over my timeline, and then ran a little stop solve, just blend it slowly in certain areas to kind of just break it up a little bit. And I decided to run Stockholm on the 1st of May, 2025. It's where I was born. It's my hometown. So this is the raw data that came out of that. So that's kind of the wind direction, normalized now to a coordinate space that makes sense in Houdini on the XC plane, from 6 a.m. to like midnight, basically. And then this here, we see here, is the wind speed mapped out. As you can see, it's a little bit, you don't know where this is really, but on the right, it's kind of over the ocean bit, so it kind of makes sense, it's windy there. And this is the temperature. So you can almost start to see the landmass there a little bit. And then I decided that maybe I could use this temperature. I can imagine that affects where the wind would blow. It would probably be colder where it's windier. So I generated some vectors just by sampling the temperature. So I just scattered a bunch of points and then using these points. So this is where I'm weird. I'm doing all of this stuff in BOPs, which is really hard to read and understand a lot of times. But all I'm doing here really, even though it may look complicated, is I'm just looking at the temperature of any given point, looking at the neighboring points, iterating through them, and then checking if there's any given point that has a higher temperature, then add it to a vector. And I also count how many times this happens in the loop. And then once you're done, once you come out of the loop, when you loop through all your neighbors, you then take that vector and divide it by the count. That gives you the average location of those points that have a higher temperature. And then you just subtract that against your position of the original point, and it gives you that kind of vector. So now we have the original, we kind of blur that a little bit, and then use the wind scale to scale those vectors. And then we also add this other temperature velocity vector into it as well. And then we add a little bit of noise as well, because we're starting with like a 10 by 10 grid. It's not the most high resolution data set. So let's do that. And then I was like, okay, now I'm on the roll here. Now I got the data. Finally, I can start doing something with this. So I was thinking, I'd still need more though. I need more than just the wind. I want to be able to use the landmass or other features of the coordinate space to drive my data. So I first tried to do a similar thing with API calls, where you would look for elevation on different coordinates, but I really quickly realized that was going to be way too slow and not work out very well. So instead, I thought I can just get the bounds of the lat long on the entire grid. So, and then remap that to a world map. You can download this really huge planetary maps from NASA and stuff that then you can just crop into it essentially. So just change the UVs of the grid to match the space that you sampled for the weather sample. So now we have this, and this is Stockholm in the middle. For those of you who haven't been, I highly recommend it. We have Finland and Denmark and Norway. We shouldn't talk about Norway, joking. And then I thought, okay, this is cool and all, but again, the data is a bit blurry, it's a bit shit. It's not going to be enough for me when I visualize this later. So I thought, what if I could do some other visualization of this? So I asked ChatGPT again, can you convert this incoming image to ASCII art for me? Do you know what that is? It's like when you kind of try to render a image without pixels, you just use symbols. Because I thought that's kind of on theme with this kind of retro computing and the manifold stuff. So I did that. That was really easy as well. So this is using hashtags and @ symbols and equal signs and whatnot to map out, again, Stockholm. And it just gives the impression of a higher resolution, just because you're kind of breaking up to more detailed little intricate symbols everywhere. And the benefit of this as well is that when you later on use it for texturing, it starts to create a fabric texture in itself that gives the impression of much, much higher resolution. So again, here's the heat. I also did the same thing here. So this is the heat map now mapped with ASCII symbols, just running it through caching out by frame, basically, and then recording it, rasterizing it in Copernicus. So now we have all the information I wanted to start building out the sim, and now it's kind of the easy part in a way. So I just pulled in all of these attributes that I wanted to look up, transfer them over to my grid, and this is happening in a time-dependent manner, so it happens every frame. So we're reading in flow, which is that temperature vector, wind direction, temperature, wind gust, and speed. Wind speed, I should say. And then we just fire it into a pretty standard Vellum solver setup. And if we dive into the Vellum solver, we have, we need to kind of update all of these attributes. So by default, the first frame is what it holds, so we kind of need to pull that in every frame. So we have this VOP here that is just loading in the attributes per frame. And then we're just using a pop wind, and that's modulating the velocities with the new vectors, and also the flow, and kind of balancing them out like you saw earlier. And then on the right, we have a SOP solver, which I like to use SOP solvers whenever possible. Inside of there, I'm basically just operating on the geometry constraints. So I just wanted to kind of ensure that where the land meets the sea of the map, basically, that area, I wanted to make sure it was a little bit stiffer and kind of pinned ever so slightly to its original position, not to kind of deform the landscapes too much. And then I also wanted to modify the rest length with the temperature. So now I ran that sim, and that's kind of what came out, more or less. And I thought, and you can see that with the kind of original velocity vectors mapped on top of it, that it kind of, you can sort of see the weather and how it changes. So without further ado, I'll show you what it actually looked like on the 1st of May 2025. And here we're using you can see the ASCII type again is now used in texturing. The orange is representing the temperature change throughout the day. And then, the land mass and everything. And then here is a top-down view. This is quite in a way it's better to see it. And this is when you realize how big the area actually sampled. So calling this Stockholm is a little bit funny, because it's more like Europe. And then we were in Barcelona, so I figured I have a few more API calls, so let's run. The next day I ran Barcelona, and I'll also run another one. So same date though, so in the same time that the other one was happening, this is here, and you can see there's a lot more orange here, which makes sense because it's warmer here. That makes a lot of sense. And then the top-down view of that as well. So this is the exact same setup again, and all I've changed was literally just the coordinate for the center of that grid, and then everything else just propagates through. And then I ran London as well, because that's where I've been living a long time. And 1st of May again. So yeah, and as you can see here, and I can confirm that this is in fact true, it's very windy in the UK. So, and not very warm either. It's like no orange at all. So this leads me on to another experiment that I did a while ago. Now we're talking about maps, see how we're transitioning. Now we're going to talk about terrain generation. I've been experimenting with vibe coding, or whatever you want to call it, where you literally don't code, you just talk to an AI and it writes stuff for you. And I had this idea to, like, normally when you generate landscapes, you start with a sculpt or a noise pattern, and then you erode it, and you define, this is on this slope angle I want trees, and so on. I thought, what if we just flip it? Like, what if we start with things we observe from the start? And I'm sure this is not a new idea, but it was new to me. Like, what if we decided wherever it is a beach tile, we know we're probably gonna be close to other beach tiles or like shallow water, and then like this. So this was my first kind of set that I started with. So very deep ocean can only be adjacent to very deep ocean or deep ocean. And then you can transition from deep ocean to ocean and very deep ocean, beach to grassland, and ocean, forest, mountains, mountain peaks. So in theory, if I have a tile that is a beach and it ends up close to a mountain peak, it will flag it as it has a lot of problems or like conflicts in its neighborhood. It would just look at the nearest tiles, and then if it was, then it would have to reset that and then expand the neighborhood and try to resolve it again. So I built this this tool together with ChatGPT again, and I have all of these parameters now that I've added all this functionality over time. It started with a very small prototype and then just slowly added to it. So we have seed values, we have resolution controls, conflict tries, we have a slider to kind of control if we favor common tiles, so it's more likely to spawn similar tiles nearby. Land bias, which is like more water, more land. And a bunch of different traversal methods to kind of like, you're solving one tile at a time, but depending on which one you choose, like which method you navigate that grid as you spawn it, it really changes the outcome. And then some upressing and other things. So let's look at an example. So this is a very low-res landscape. As you can see here, we see the mountaintops. And in some cases, this has a lot of conflicts right now because it doesn't have any conflict resolution on it. So you have some really high mountains just next to really deep oceans, which is not a desired effect in this case. So if we add just 5 conflict iterations on this, you can sort of see how it's starting to clear that up quite a lot. And if we go 25 steps, now we've essentially resolved all of the conflicts, and it generates, and as you say, the dark green is like forests and stuff. I didn't specify these colors either. That's part of the tool set, and it's represented as a grid. And then if we uprest this, which the upressing happens in a way that where for each little tile, we just subdivide it into 4 and reset all but one of them, and that inherits from the previous level. So that way you kind of retain a lot of the same features because it's more likely to gonna spawn similar tiles again as you uprest. So here's 2 uprest, and then 3, 4, 5. And if we look back at the first and the last, it really retains the original intent of the low-res thing, and it's kind of interesting. And the more you play around, you start to get the intuition for what the different parameters do and how they work. And if we now go back to the original unresolved one, and instead of resolving at this resolution, we just uprest, and as we uprest, it automatically runs those conflict tries. And we do the same thing again 5 times. We end up with still a very, very consistent to the original iteration, but now we have more variation in thickness because we didn't resolve those things at the low resolution. So both valid, but I think if you look at them, it feels more natural when you kind of resolve it as you uprest. And it kind of goes with a lot of stuff in design in general, like starting with a rough sketch and then refining it makes more sense. If we look at the sea land bias, this is what that does, you know, the more you increase it, the more land you get. Go figure. Favor common, this is like, as I mentioned, it will have a slight bias towards common similar tiles. And you can really see that on the higher settings, like when you go higher, it really becomes prominent, especially up there. And then the neighborhood size is basically, if you're just looking at the very nearest neighbor, above, left, right, south, versus if you expand that neighborhood, you then count all of the conflicts and figure out which are the best methods of resolving it. Or like which have the least conflicts, considering a bigger neighborhood. So if you start with 0, it's just noise, as you can imagine. But as soon as you go to 1, you start getting these environments that kind of emerge. And if you increase it, it's almost like you're zooming in. It's almost like the landscape becomes more and more, it's like you're zooming in from space. It's just, features become like they just emerge from bigger patches. And if you keep going, it really is just that. You know? So this is with this initial rule, or still initial rule set. But then I wanted to push it a little bit further, so I was like, okay, ChatGPT, you know this kind of rules that we've been using. Make those our fallback rules. Let's add external rules. Let's see if we can like figure out a way of expanding this. So I literally just copied the entire script and say, after that had been implemented, and said, now read this script. You can see you can load in JSON files here with like new rule sets. So can you make me a landscape based on Iceland or whatever? So that's Iceland. It has a lot more lava and mountainous terrain and black beaches and stuff like that. And then I did one, like, oh, this is Mars, you know, rainforest, and this is like some sort of weird alien landscape. So yeah, that was just a little bit of a quick run through of some experiments that, you know, different way of using AI, I guess, that isn't from prompt directly to pixel, but we've also been using it a lot for like other helpers within the company, like pipeline tools and stuff like that. And I highly recommend, if you're gonna try it, use the Python SOPs and stuff like that instead of trying to do it in Vix, because there's a lot more data sets that are out there for that. So we have a little bit of time, so I'm just gonna run the manifold, and then we can do some questions. All right. All right.
It always feels to me like you can see a little bit into Simon's brain through his work. Any questions?
That was boring, right?
I know you've got a question. Think it through, then release it. There you go.
Hi, Simon. I love the presentation. I have a question. You talked about you used ChatGPT to build tools for pipeline within Panoply. So can you develop a little bit more about that?
Yeah, so it's always it's just about removing friction when saving out files and where things go and so on. So we have a certain file structure or folder structure that we try to attend to, but a lot of times it gets a bit annoying to make sure you save in the right places. So a simple example would be that, essentially. We look at the folder structure where the HIP is saved, find the actual project name from the folders, and based on how that's formatted, and then create automatic paths and read out. We also had like a script for like reading metadata of EXRs when they were like created, and then create dailies with like a little bit of like text and stuff on top of it, so that it would like put it in the right dailies folder and stuff like this. Little helpers that just take some of the busy work out of, like, at the end of the day when you're really tired and you're gonna send off your renders and stuff. It was just stuff like this primarily, and then, you know, we I think that's the best example I can think of off the top of my head of stuff we use that. And it's specifically with Python and expressions, you can do a lot. And I don't know a single bit about Python, but you can actually get stuff to happen with it, like if you have a little bit of patience and take it step by step, much like you would if you were programming it yourself. Start with a basic example and then build upon it.
Yes, thank you so much.
Anyone else? Give me a second. Going once, going twice. Simon, thank you so much.